Hi, in this video we proceed with two-variable regression model analysis. So to be more precise, what we're going to discuss today is ordinary least squares estimation and assumptions to be met in order to have estimator nice, efficient, and unbiased. So to recall what we discussed last time, here you can see sample regression line, which stands for the relationship between the independent and dependent variable. So basically, this is expected value of y conditional to this value of x. So the value of intercept will be equal to beta 0, or saying more formally, if the value of the independent variable is equal to 0, the expected value of the dependent variable will be equal to beta 0, and the slope of regression line is equal to beta. So as you remember, there is always a difference between the estimated value of y and the actual value of y. So for instance, for this value of x, I expect to see this value of y based on this regression line. However, the actual value of y corresponding to this value of x is here, is greater. So the difference between actual and predicted value of y is captured by stochastic error term or disturbance term. So yeah, there might be numerous reasons, for the difference between estimated value of y and actual value of y. For instance, there might be some other potentially important variables which determine the value of y but are not captured by this model. My model formulation might be bad, so I don't know. Maybe there shouldn't be the linear relationship between y and x, but I don't know. Any other kind of trend. So maybe it's because of model misspecification. Maybe there is just some intrinsic randomness which cannot be captured by any kind of explanatory variable. So yeah, there are many reasons, but the conclusion is like this. You can never design a regression model, where all the predicted values of y will be just equal to actual values of y. So, keeping in mind this idea, you can justify, the key idea behind the ordinary least squares estimation. So, as I said, U stands for the difference between estimated value of y and empirical value of y. So, you can never have it equal to 0. However, what you can do is to try to minimize it, to make it as small as possible. However, when we design a model, we keep all of those, observations in mind. So it's not only about single stochastic error term minimization, it's about minimizing the sum of all the error terms. Also, keep in mind that we are not really interested in the direction of this difference. So for us, it does not really matter whether empirical value or actual value of y is above or below the estimated value. It's all about magnitude. So if we are interested only in magnitude, and we can neglect direction of this deviation, so let's say sign of this deviation, to ignore the fact whether it's positive or negative, we shall put the value of the stochastic error term to square. So in this case, it does not really matter whether you have deviation of +1 or -1. If you take everything to the power of 2, then you will get 1 at the final result. So, this just allows you to capture this fact that you're really indifferent, about the direction of this difference. Just about, so you're interested only in magnitude. So, keeping this in mind, the idea of ordinary least squares estimation is to design such a regression line, for which the sum of square terms of stochastic error term would be minimized. So there are several assumptions to be met, in order to design a model with valid and reliable output, which can be then used for testing research hypotheses. So first we have to assume that the model is linear in parameters. So linearity in parameters means that all the coefficients in front of the independent variables are linear. So here you have beta 1, not beta 1 square or not beta 1 log of beta 1. However, it does not mean that the model has to be linear in variables, as we're going to discuss in a second. So before we proceed to the rest of assumptions, I will show this based on the model I have estimated using RETL, and as usual you can find the link to the data below in description of the video. So let's discuss a bit of economic theory, before proceeding to regression analysis. So, because, again, as we discussed before, econometrics is definitely not about data mining. So when you do econometric estimation, you have to keep in mind prior theory in order to, prior theory, some theoretical model to justify the functional form of the regression model and your research hypothesis. So here we have this piece of economic theory which will be relevant for further analysis. So Kuznets curve is basically this curve, and the idea behind this is that there is non-constant relationship between income inequality and income per capita. So the idea is like this. When the level of per capita income is relatively low, so those countries with relatively low level of per capita income are emerging economies and developing economies with relatively low stock of capital and so on and so forth. Income inequality will increase with the increase in per capita income. So basically Kuznets explained it by the fact that industrialization, which accompanies the process of per capita income increase at the early stages of development, implies increase in the degree of income inequality. Because with industrialization, capital owners get more bargaining power, so they accumulate their income, and as the result there is increasing income gap between capital owners and labor force. So this trend continues until economy reaches some critical level of per capita income. So basically here we have maximum of income inequality, and once this income level is achieved, then income inequality will decrease with increase in per capita income. I don't know, when countries achieve certain level of development, actually I know how to explain it, I just do not remember how Kuznets explained it. But you've got the idea, yeah? For instance, you can analyze countries such as, I don't know, Canada, Australia, or any other developed country except for the United States. So when certain level of economic development is achieved, and certain level of per capita income is achieved, then government can spend more money on social security benefits, support of people with low income. Government has more money for investment in education and so on and so forth. So basically it does not really matter, probably it's not relevant at this point, but the idea is like this. After some level of per capita income is achieved, income inequality will decrease with increase in per capita income. So once again, up to some point, there is a positive relationship between these two variables. After some point, there is a negative relationship between these two variables. So, keeping in mind this piece of theory, this is the way in which you should describe econometric regression. So definitely, this is not a linear trend, and you can use some theory in order to justify your idea. So what I mean is that what we're going to discuss in a second is based on the initially misspecified model. So I did this intentionally, describing the relationship between income inequality and per capita income as a linear relationship, while knowing that definitely it's not a linear relationship. So this is rather an inverse U-shaped curve. So here are the result of this regression. Again, for this, I've taken income inequality data set, and I took Gini as the dependent variable and GDP per capita as the independent variable, just to estimate the relationship between income inequality and per capita income, when the latter stands for the independent variable. So again, as I said, this model is misspecified intentionally. So this is how my regression model should look like, in accordance with economic theory, and this is how my regression model actually looks like. So here you have estimation output. We will get back to this. And here you have the second assumption. So in order to estimate a valid model with reliable output, like basically a reliable estimator or blue estimator, okay, we will get back to this, the following assumption has to be met. There should be no dependency between the value of x and error term. So basically no dependency between the value of independent variable, in our case GDP per capita, and the value of the stochastic error term or residual. Okay, basically it's not the same, but whatever. At this point it's fine. So basically it means that covariance between independent variable and error term u has to be equal to 0. And okay, maybe I will estimate this model first. Sorry, give me a second. Okay, so as you remember, file, open data, user file, desktop, teaching, introduction to econometrics. Oh yeah. So if you cannot see the file, probably you have to specify the format of this file. Okay, so this is inequality training set, open, okay. Yes. Oh. Okay, so please remember that it's kind of a useful habit to specify the character of your data set in Gretel. So I refuse to do this initially. Yes, I want to give data panel interpretation. So this is panel data set, index variables, ID year. Yes, apply. It's fine. Okay, so looks fine. So model ordinarily squares, Gini, GDP per capita. No. Okay, so as I said, Gini will stand for the dependent variable GDP per capita will stand for the independent variable, and constant is just beta 0. Okay, so we have 1544 observations, looks fine. So please save residuals. You will need this for the further analysis. Okay. And as usual, this is how you design a regression line quickly and effortlessly in Gretel. Yes. Okay, so this should be identical to what you see in this slide. So proceeding to this assumption, how you can analyze the relationship between the value of x and error term. So obviously, if there is actually the relationship between the value of x and error term, then assumptions which we're going to discuss in a couple of slides will not be met, and this will be reflected by the value of corresponding post-estimation test. But again, you can do some simple stuff. So you saved residuals, like the value of residuals obtained for this model, or the values of the difference between predicted and actual value of y. So what you can do is actually try to plot the graph of residuals versus GDP per capita. So in this case, you will have to get back to model. So graphs residual plot against GDP per capita. So this is what you get. So again, this is by no way any kind of formal analysis, but sometimes visual analysis of the data might be helpful. So the second assumption tells you that there should be no relationship, no dependency between the value of x and error term. So they should be independent from each other. But, even looking at the regression line, like you remember that the distance between empirical, like actual value of Gini coefficient and predicted value of Gini coefficient will stand for the error term. So even here, you can see that for the relatively small values of GDP per capita, you have relatively big difference between the actual and predicted value. So for small value of GDP per capita, you have big residuals, and for bigger values of GDP per capita, you have smaller residuals. It's, also visible on this graph, because here you just have residuals plotted against GDP per capita level. So again, for relatively small level of GDP per capita, the value of residual is huge, and for the relatively big value of GDP per capita, the value of residual is rather small. So here you can tell immediately that the second assumption is not met. So actually there is the dependency between the value of independent variable and stochastic error term. So the bigger is the value of independent variable, the smaller is the value of stochastic error term. And then you have some strange outliers. Okay, whatever. But I believe you've got the idea. So as I said, you misspecified the model initially. So instead of having this relationship described by inverted U-shaped curve, we assumed linear relationship between income inequality and per capita income. And, that's why basically you have this assumption not met. So yeah, just to underline this, most frequently, not meeting this assumption results from model misspecification, like assuming a wrong functional form of the regression line or regression curve. No, technically it will be curve, but okay, whatsoever. Okay, so the third assumption tells you that there should be zero mean value of stochastic Okay, that's better, of stochastic term disturbance. So given the value of the independent variable x, the expected value of the error term should be equal to 0. Like informally, you remember we have positive error term, negative error term, positive error term, negative error term, and so on and so forth. So basically it means that on average, we know they have to cancel out each other, and the average value of the error term should be equal to 0. So again, here you can see the regression line. So in this case, definitely the distance between the empirically observed value of Gini coefficient and the predicted value of Gini coefficient, I wouldn't say, it's distributed symmetrically. So at this portion of the graph, yes, you have like a lot of positive values and then a lot of negative values, or the values below the regression line, and then you have a lot of negative values and not that much of positive values. So in contrast, if you draw some hypothetical regression line which fulfills the third assumption that the mean value of error term should be equal to 0, then it should look, something like this. Again, it's very schematic and simplistic depiction, but you've got the idea. So each positive value should cancel out the negative value. In this case, definitely you have negative values. You have much more negative values than positive values, and it does not look like, this assumption is fulfilled. But as I said, this assumption will also affect the next assumption we are going to discuss in a second, and this will be visible when you do some formal post-estimation test. So this is just some attempt to show you how misspecified how it looks like under misspecified regression model. Okay, so this one not fulfilled. Assumption 4, homoscedasticity or constant variance of the stochastic term. So basically it means that we assume the variance of the error term or U or stochastic term to be independent from the value of independent variable. So again, here you have the actual value of Gini coefficient against the predicted value of Gini coefficient. Like for this, you can also use Gretel. You get back to model, graphs, fitted actual plot. Yes, actual versus fitted. So here you have it. So basically, this is actual value of Gini coefficient from the data set, and on the horizontal axis, you have predicted value of Gini coefficient. So again, in this case, each time you have this cone pattern on this graph, like, relatively small distance, then this distance increases, or vice versa, then actually it's kind of suspicious, and it suggests that probably this model, okay, so probably we deal with heteroscedasticity. So the variance measure of dispersion of the error term is not constant, and it actually depends on the level of x. So luckily for you, you can, analyze this formally. Like for instance, using White's test for heteroscedasticity. So to do this test, you get back to Gretel model. Okay, here is model. Test, heteroscedasticity, White's test, ta-da. So again, we will get back to this when we analyze confidence intervals and so on. But here, zero hypothesis of this test is that there is no heteroscedasticity. So zero hypothesis is that variance is indeed constant. So with p-value equal to 0, you can definitely reject the zero hypothesis. So this model is indeed heteroscedastic. Actually, I'm not sure whether the model is heteroscedastic or the error term is heteroscedastic. Okay, whatsoever. So definitely we deal with heteroscedasticity here. So, that's why, although visual analysis of the data is not enough to conclude, to make any conclusion about the presence of this problem, it might be, the first step to detecting this problem and probably some methods of solution as well. So just to sum up, if you misspecify the model, you will not have the second or third or both of these assumptions met. If you do not meet these assumptions, then probably you will you will also not meet assumption about homoscedasticity, and then basically your model is a trash. So if there is heteroscedasticity, again, we will get back to this, how to fix it and how to correct it. But basically the model with heteroscedasticity is like this. Although it might not affect the value of coefficient, it affects the value of the standard error. So it makes p-value artificially low and might create wrong impression that your variables are statistically significant, while they might not be statistically significant. So to summarize, there should be no heteroscedasticity. If you designed a regression model and there is heteroscedasticity, then probably you misspecified something at the very beginning. So you have to revise economic theory, you have to revise the choice of your variables, the way you specify variables, and so on. Okay. Assumption 5. There should be no autocorrelation between the disturbance or error term U. So, in very simple words and very informally, there should be no dependency between error terms. So this is especially important when you analyze time series and panel data. So in this case, in order to I will just show you how, you can analyze it based on some graphs, like how you can do simple visual analysis. So for this, you get back to Gretel. Here I have my residuals. I add lag of selected variable. So basically the value of residual in the previous period. And I run a simple model. So here I have residuals against Give me a second, it's not visible for some reason. Oh yeah, okay. Now I remember. So this is some general bug for Gretel. If you calculate residual here, there might not be visible in the range of, variables to choose. So in this case, you can specify lag of dependent variable. Okay, the first lag. So yeah, here I will analyze the dependency of the value of residual on the value of residual in the previous period. Okay. Okay, but this is not what I'm interested in. I want a graph, and graph is here. So on x-axis variable, I will have residual in the previous period. Residual, okay. Ta-dam. Okay, so as you can see, there is definitely a relationship between residual in period -1 and t-1 and residual in period t, as you can see on this slide, by the way. So if you have something like this, if you see something like this, then there is autocorrelation. So the value of error term in the period t depends on the value of error term in the previous period. So the problem with autocorrelation is very similar to the problem with heteroscedasticity. When you have autocorrelation, your model is a trash. So you cannot really treat it as some reliable source of information, because autocorrelation makes p-value artificially small, and again it might create a wrong impression that variable is statistically significant, while it's not statistically significant indeed. And you can try to detect autocorrelation using different tests. Like for instance here, Durbin-Watson statistics will indicate the presence of first order autocorrelation. Like it's definitely less than 2, so it should be positive, as you can see on this graph. But we will get back to this when we discussed, different post-estimation tests and methods to fix the regression. So the sixth assumption tells you that the number of observations should be greater than the number of parameters to be estimated. I believe it's pretty intuitive. But also please keep in mind that the general rule is the more the better, because it makes your sample more representative and also it increases the number of degrees of freedom. So finally, according to Gauss-Markov theorem, if your estimator beta is linear, if it is unbiased and efficient, so the value of estimator beta is equal to the true value of estimator and the variance is minimized. So in different words, if you have met all the assumptions listed and described above, then your estimator is indeed blue, which I mean by nice, efficient and unbiased. And you can use your model for, testing hypotheses as a source of information about coefficients and other stuff. Okay, so standard errors stand for the measure of estimators beta 0 and beta 1 reliability. Standard error is calculated as the square root of the sum of square terms of all the residuals divided by n minus 2. n minus 2 is known as the number of degrees of freedom, and n stands for the number of observations in your model. So very informally, standard error tells you how well changes in independent variable of your choice can explain the changes in the dependent variable. So the smaller the value of standard error is, the more reliable is your estimator. So when it comes to standard errors, they are always displayed in the table with estimation output. So for instance, for our variable of interest, GDP per capita, the value of standard error is 0.01. So what I'd like to mention is that there is no commonly accepted rule on the value of standard error. So first of all, it's measured in the same unit as the independent variable of your choice. And second, the value of standard error alone is not enough to make any conclusion. So what you have to analyze is the ratio of coefficient and standard error, and also the number of degrees of freedom, so the number of your observations, minus 2. However, we will proceed to this, so there is no... Okay, and the final thing to discuss is model's goodness of fit measure, or R-squared. So please take a look at this graph. Orange line will stand for the regression line. So for instance, for this value of the independent variable, this will be the corresponding value of the dependent variable. This line stands for the value of population mean, like average value of the dependent variable calculated for the entire population. Intuitively, it will not depend on the value of the independent variable. And finally, here we have actual value of y. So as you remember, the difference between estimated and actual value of y is called residual or error term. Like there is a difference between them, but it's not that important at this point. So basically, when you calculate the sum of squared residuals for all the model, you will get RSS, or residual sum of square, and it can be described as the proportion of the dependent variable's variation which cannot be explained by the model. So this difference which arises from residual, which is caused by questionable theoretical assumptions, misspecified model, wrong data, or any other relevant reason. The difference between actual value of y and population mean will stand for the total sum of squares. Again, in this case, you take all those differences, define the square, and summarize, because we are not interested in direction, just at the magnitude. And the difference between, total variation and unexplained variation is explained variation. So this is the proportion of dependent variables variation which can be explained by the model. So actually your model explains the difference between population mean and predicted value of y conditional to some value of the independent variable. So the bigger this share is, the better, and basically this is captured by the r squared. So r squared can be calculated as explained sum of squares divided by total sum of squares, but actually in this case you have no information, you might have no information about explained sum of squares. So this formula can be summarized to the follows. So basically 1 minus RSS over TSS will stand for the proportion of variation which is explained by the model, because you subtract proportion which is not explained from 1. So the bigger value of r squared corresponds to the bigger explanatory power of the. For instance, in this case, the value of r squared is equal to 0.206. So my model explains approximately 21% of dependent variable variation. Sorry, 21. I'm not really good at rounding. So this is the idea. If I take the value of the independent variable and I analyze the corresponding value of actual y and predicted y, then I will see that the percent of the explained variation, like this, out of total variation is equal to 20% approximately. Okay, so your task is to analyze any linear regression. For instance, you can take regression from the previous assignment. Analyze the goodness of fit of your model. You have to use plots and tests discussed in this tutorial in order to define whether all the needed assumptions are indeed met. And based on this, you have to conclude whether the obtained estimator is indeed blue. So that's it, and thank you for watching.